Everybody, so in this video, we're going to talk a little bit about inscribed and circumscribed shapes. So here you can see that we have a circle inscribed in a triangle. When we use the word inscribed, we mean that it's drawn inside another shape so that it's completely touching the shape that it's drawn inside of. Notice how this circle is inscribed inside the triangle. So it's completely touching with no space all of the sides of the triangle. Over here, we have a circumscribed circle. That means that the circle is drawn around the triangle so that it completely touches every vertex of the triangle with no spaces in between. So the big difference between inscribed and circumscribed, inscribed means something is drawn inside another shape. Circumscribed means that something is drawn around another shape, as you can see from the pictures. We have an inscribed circle inscribed inside a triangle, and we have a circumscribed circle. The circle is circumscribed around the triangle. In the diagram below, triangle ABC is circumscribed about circle O, and the sides of triangle ABC are tangent to the circle at points D, E, and F. If AB is equal to 20, AE is 12, and CF is 15, what is the length of AC? So this is what we are trying to find. Take a second. Can you find the length of BE? If you said 8, you are definitely correct, since BA or AB is 20 in total. If we have a tangent, two tangents coming out of the same point, if BE is 8, BF will also be 8 because two tangents coming out of the same external point are congruent to each other. So if we know that FC is 15, what's DC? If you said 15, you are correct. And if we know that AE is 12, what's AD? Well, if you said 12, you are correct. Once again, two tangents to a circle from the same external point are congruent. So we have the length of AC is 27 units. So instead of saying that triangle ABC is circumscribed about circle O, we could also say that circle O is inscribed in triangle ABC because it is inside triangle ABC. Here we have another example. As shown in the diagram below, quadrilateral DEFG is inscribed in a circle, and angle D is 86 degrees. We need to determine and state the measurement of arc GFE. So we need this arc from G to F to E. Take a look at the angle that we're given, angle D. What kind of angle is angle D? Think about where its vertex is located. If you said an inscribed angle, you are correct. It's an inscribed angle that intercepts arc GFE. And remember that inscribed angles are half the measure of their intercepted arcs. So if we know that angle D is 86 degrees, what is arc GFE going to be? If you said 172 degrees, that would be correct. From here, it's asking us to state the measurement of angle F. What kind of angle is angle F? Think about where its vertex is located. If you said inscribed angle, once again, you are correct. Angle F is an inscribed angle intercepting arc GDE. We know that all the arcs in a circle add to 360. So if we already know that the arc in red, GFE, is 172, we can do 360 minus 172, and I got 188 degrees for arc GDE. Since inscribed angles are half the measure of their intercepted arcs, half of 188 is 94. Take a second and add together 86 and 94, the two opposite angles in this quadrilateral. You probably got 180 degrees. Do you remember another word for two angles that add to 180 degrees? Wonderful, supplementary. So this is actually a property of shapes that are inscribed in circles. First of all, when a shape is inscribed inside a circle, we call it a cyclic quadrilateral. One property of cyclic quadrilaterals is the property that we just saw here, that opposite angles in a cyclic quadrilateral are supplementary. And the exact technical definition of a cyclic quadrilateral is a quadrilateral that can be circumscribed. So notice that this quadrilateral has a circle drawn around it, so it can be circumscribed so that it touches each vertex point. And notice that when we circumscribe the quadrilateral, when we draw a circle around it, the circle touches every single vertex of the quadrilateral. So that's why we call it a cyclic quadrilateral. That's what the definition of a cyclic quadrilateral is. Take a second and answer the question shown here. It's a multiple choice question, so you're choosing from answer choice 1, 2, 3, or 4. Please explain why you picked the answer choice that you did, and try to use some new vocabulary that you've seen in this video in your explanation. So the correct answer is answer choice number 4, opposite angles in a cyclic quadrilateral. That means a quadrilateral inscribed in a circle so that its vertex points touch the circle. Or another way of wording it is a quadrilateral that can have a circle circumscribed around it so that all of the vertex points are on the circle. So this is a cyclic quadrilateral, and a property of cyclic quadrilaterals is that the opposite angles are supplementary. We can also think of it in terms of inscribed angles. Since J, let me highlight that better, since angle J is an inscribed angle. So that means if its intercepted arc is x, J would be half of x. And M is also an inscribed angle. So that means if its intercepted arc is 360 minus x, because we know that all the arcs of a circle add to 360. So if this is like 20, which it's not, we would find this by doing 360 minus 20. This angle over here would be half of 360 minus x. And half of 360 is 180. So it would be 180 minus the other angle. So that shows that these two angles would be supplementary. Moving forward, take a look at number 1. Try to find x and y. We can use the property of cyclic quadrilaterals here that opposite angles are supplementary in order to find x and y. I can do 80 plus y plus 30 equals to 180. And when you solve that equation, you should get y is equal to 70. I can also say that x minus 10 plus 75, the other opposite angles, are equal to 180. And when you solve that equation, we get 115. And we can just double check really quickly. If I plug in, let's plug in y. So that's 70 plus 30. That's 100. And 100 plus 80 is 180. Should be the same thing if I plug in 115 for x. If I evaluate what angle D is and I add it to angle B, I should get 180. Take a look at 2. Show that ABCD is a rectangle. Try your best to explain why this is true. Think about what goes into showing that something is a rectangle. Okay, so we know that O is the center. So I know that this arc is going to be 60 degrees because central angles are congruent to their intercepted arcs. These are vertical angles. So once again, 60 and 60. Now, I know that these are congruent arcs, and I know that parallel chords intercept congruent arcs. So that tells me that AB and DC are parallel to each other. Now, if this is 60 and this is 60, these two vertical angles need to be 120 degrees to make 180. And once again, central angles are congruent to their intercepted arcs. And as mentioned before, parallel chords intercept congruent arcs. So we have both pairs of opposite sides are parallel, making the quadrilateral a parallelogram. Now, to show that it's a rectangle, we need to show that it has at least one 90-degree angle. A parallelogram with a 90-degree angle is a rectangle. So take a look here. I'm just using angle A. I could use any of the 4 corner angles of this parallelogram. We haven't proved it's a rectangle yet. Angle A is an inscribed angle. So that means it's half the measure of its intercepted arc. Its intercepted arc is arc DCB. And arc DCB is 180 degrees. So half of that is going to be 90. Arc DCB is a semicircle. Angles inscribed in semicircles are right angles because half of 180 is 90 degrees. So we showed that it was a rectangle. A parallelogram that has at least one right angle is a rectangle. Take a look at number 3. Feel free to pause the video to read the question and then try to answer it. Is TAEO a parallelogram? Justify your answer. Okay, so we know that midpoints split a line segment into 2 congruent parts. And then we have tangents coming out of the same point, so they're congruent. Here we have 2 tangents coming out of the same point, so once again, congruent. So all 4 of these are congruent to each other. Here we have tangents coming out of the same point, so congruent. Tangents coming out of the same point, so congruent. So all 4 of these are congruent to each other. So I missed before that the question said to find the perimeters, so I just filled in the measurements of the segments and added them together, and you should get 64. As you can probably tell, TAEO is not a parallelogram because in order to be a parallelogram, both pairs of opposite sides would have to be congruent to each other. And as you can see, side TA is 20, but side OE is 12. Side TO is 16. Side AE is also 16, but that's not enough because both pairs of opposite sides need to be congruent to make it a parallelogram, not just one pair of opposite sides. The last thing we're going to talk about is inscribing a circle inside of a triangle. So we're going to construct something called the incenter, which is going to be the center for inscribing a circle. So the way that I'm going to do that is I'm going to bisect 2 of the angles of this triangle. And where the angle bisectors meet, that's where the incenter is located. So if you're unsure what I'm doing, feel free to reference Regents Review number 1, which has the steps for constructing an angle bisector. You can definitely bisect all 3 angles in the triangle to get a more accurate incenter, but 2 are definitely enough, not just 1. We need 2. We need to see an intersection. Okay. Let me finish this one up really quickly. Oh no, my compass doesn't want to write. There we go. So difficult to move the compass on the computer. And we will do this construction in class as well so that you can practice it along with me. Oh no. There we go. Finally got that to make an arc again. So my arcs are a little bit messy because I'm doing this on the computer. But as you can see here, I have a point of intersection. And let me try to get a dot for that. I don't think I can get the dot. I'm going to dot that as best as I can. And that's my in center. I'm going to use that as the center of my circle that I'm going to inscribe inside the triangle. Now, as if our angle bisectors weren't enough, we have the center of the circle that we're going to inscribe. We also need the radius so that we can actually construct the circle. So in order to do that, I'm going to construct a perpendicular line from the through the incenter. So what I'm going to do is construct a perpendicular bisector. Let me do this as best as I can, as quickly. And on the computer, it does come out a bit messy, so I do apologize for that as well. Let me use a different color line. There we go. So now I should be able to inscribe my circle. I'm going to put my compass on the incenter. I'm going to just open up to the radius, the length of the perpendicular. And then from here, let me use a different color. I'll use yellow. There we go. I'm going to construct an inscribed circle. So it's not exactly perfect. We know that it should touch the edges, but once again, my compass kept moving on the computer. We'll do this in person as well, but that's the idea of it. Construct the angle bisectors to get the center, the incenter we call it. That's the intersection of the angle bisectors in a triangle. That's the center of the circle. Then construct a perpendicular so that you can use that as the radius of the circle. We can also construct the circumcenter of a circle, which we use to circumscribe. We can also construct the circumcenter of a triangle, which we use to circumscribe the triangle. So take a second and see if my arcs that I'm making look familiar. Once again, I'm trying to do this super quick, but see if you can guess what construction makes up the circumcenter. So if you were guessing perpendicular bisector, you would be absolutely correct. So once again, it's more accurate if I do the perpendicular bisector for all three sides, but I only have to do it for two to get a pretty good depiction, but three would be the most accurate. Okay. Now I can just simply draw a line through that. I think I need to extend this one a bit more. I should have extended it more to begin with. There we go. And now I see the intersection point. It is right here. So I'm going to take my compass and I'm going to put it on that intersection point, which we call the circumcenter. And I'm going to just open my compass to one of the vertex points of the triangle, and I should be able to circumscribe the triangle. And there we go. We'll also do this one in class.